Hello, this is Math 131, section 5.1. This section deals with what we call number theory. Okay. So it's a study of numbers and their properties. So we're going to start by looking at our counting numbers, our natural numbers, which we already looked at, right? So our natural numbers is that set capital N, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. Okay. When we multiply natural numbers together, we get what we call factors. Okay. So natural numbers that are multiplied together are called factors. Okay, of the product. Okay. So a natural number may have many factors. Like for 18, okay, we've got 1. Well, 1 goes into all the natural numbers, right? And then also 2, because 2 goes into 18. 3 is a factor of 18. 3 goes into it. 6, 9, and also 18 itself. So for any natural number, we always have this number, 1, and the number itself. So for 18, we always have 1 and 18, but we also have 2, 3, 6, and 9. Okay, let's talk about divisors. Okay, if A and B are natural numbers, that they're 1, 2, 3, 4, 5, 6, etc. We say that A is a divisor of B, or A divides B, which we use as this symbol right here, this bar, A, kind of that straight up and down bar. If the quotient of B divided by A has a remainder of 0. Okay. In other words, B is divisible by A. Okay. So we could say, like, in particular, that if we take B divided by A, we get a remainder equal to 0. Okay. So that's what we mean by saying that A divides B. Okay, that A goes into B perfectly. Okay, prime number is a natural number greater than 1 that has exactly 2 factors, itself and 1. Okay, in other words, there are no other numbers that go into it. Like, for example, 7 is a prime number because only 1 and 7 go into it. 2 is actually a prime number. But any other even number is not, because 4, 6, 8, 10, 2 goes into it. Okay. A composite number is a natural number that is divisible by a number other than itself and 1. In other words, there's other numbers that go into it. Okay. The number 1 we kind of throw out because it's neither prime nor composite. Okay. We call that a unit. So 1 is sort of an exception, but maybe examples of prime numbers here. I'll just list some of the prime numbers up here. 2, 3, 5, 7, 11, 13, 17, 19, etc. These are prime numbers. Okay. Composite numbers, we're not going to use 1, right? So composite numbers would be 4, 6, 8, 9. That's our first odd prime number. Well, yeah. And then 10, 12, 14, 15. These are all numbers that have other factors. There's other numbers that go into these. Like 2 goes into 4, 2 and 3 go into 6, 2 and 4 go into 8, 3 goes into 9, 2 and 5 goes into 10, 2, 3, and 4 and 6 go into 12, 2 and 7 go into 14, 3 and 5 go into 15. But for these prime numbers, only 2 and 1 go into 2, only 3 and 1 go into 3, only 5 and 1 goes into 5, only 7 and 1 goes into 7, etc. for those prime numbers. Okay, so we see the difference there. Okay, so here's some rules for testing whether numbers are divisible by a certain number. Okay, rules of divisibility. So if we wanted to see if something is divisible by 2, we just see if the number is even. Okay, so for example, 924 is even because it ends in an even number. Basically, that's all you have to look at is the last digit and see, is that 2, 4, 6, 8, or 0. Okay. 3, you may not know this, but 3 is, if a number is divisible by 3, if we take the sum of the digits is divisible by 3. Okay. So, for example, for 924, we're going to add 9 and 2 and 4, and that gives us 15. Okay. And then we see 15 is divisible by 3, and that means that 924 is divisible by 3. So all I have to do is add the single digits and see if 3 goes into it. Okay. And if your number's still too big, then you can do it again. Like we can add 5 and 1 and get 6, and 3 goes into 6. So that means it goes into 15 and also goes into 924. Okay. For 4, okay, we can say the number formed, let me highlight this, the number formed by the last two digits of the number is divisible by 4. Okay, so for 924, we only have to look at 24. We don't have to look at the 9 because all hundreds are divisible by 4. So we can just take off all the hundreds and and that's everything above the second digit. So 24, 4 goes into it times 6, right? Another thing we could do is take half the number and see if it's still even. So if we take half of this, we get 462, which is still an even number. That means we can divide it by 2 twice, which is the same as dividing by 4. Okay, 5 you probably know. If a number is divisible by 5, the number just ends in 0 or 5. 5, 10, 15, 20, okay, etc. So 265 ends in 5, is that divisible by 5? Okay, so these are some of our rules of divisibility. Okay, continuing for 6, okay, remember 6 is 2 times 3, so we can just say the number is divisible both by 2 and 3, okay? And how do we test both of those? Well, first of all, we can say it's even, so it ends in a 4, that means it's even, so it's divisible by 2, and then to check for 3, just add the digits, right? And we get 15, right? So we know it's divisible by 6, it's divisible by 2 and 3. For 8, the number formed by the last 3 digits is divisible by 8. So let's look at a 4-digit number. For 5824, we just have to check the last 3 digits and see if 8 goes into that. And 8 goes into that 103 times. Okay. Another way to do that is see if we can divide it by 4 and by 2. Or we can take half of it 3 times, basically. Okay. Because 2 times 2 times 2 is 8. So if you can take half of that 3 times and still get a natural number, then it's divisible by 8 as well. Okay. For 9, the sum of the digits is divisible by 9. So this is just like the 3. Okay. So if we add our digits and we get something that 9 goes into, 8 plus 3 plus 7 is 18, and 9 goes into 18. So we know it's divisible by 9. So this is just like 3, except we're going to divide by 9 instead. We add the digits. Okay. And 10 we probably know, right? It's just the number ends in 0. Okay. 290. Anything that ends in 0 is divisible by 10 because that means there's no 1s and you just have 10s. Okay. Okay, so let's talk about the fundamental theorem of arithmetic. That says that every composite number, it's not a prime number, can be expressed as a unique product of prime numbers. Okay, and we call that the prime factorization. Okay, so that means we can break down a number into prime factors, and it's unique for each number. So, for example, 24 is 2 times 2 times 2 times 3. Okay, or 2 cubed times 3. Remember, the exponent means we're multiplying 2 3 times. So 2 times 2 times 2 times 3 is a prime factorization of 24. Okay, we don't use the 1 in this case. Okay, so this is our ways of finding the prime factorizations. Our first method is called branching, and it's like a tree method. First of all, we select any two numbers whose product is the number to be factored. So if we started with 48, we would say like 8 times 6. Okay, and then if the factors are not prime numbers, continue factoring each number until all the numbers are prime. So we create a tree. Okay. So for example here, let's look at 1500. That's 15 times 100. Okay, so those are our two factors. And then 15 we can break down as 3 times 5, and those are prime. So when they're prime, you can just circle them. I'd circle them here. Okay, and then 100 is 10 times 10, so we can break that out as 10 times 10. And then we have to break the 10s out into 2 times 5. Okay, and then when you're done, you don't have to stretch these down. Just circle them if they're prime numbers, and then you have these leaves that are circled. So we get a 3, 5, 2, 5, 2, 5. Okay, so that's 2 times 2 times 3 times 5 times 5 times 5. See, we have 3 5s and 2 2s and 1 3. Okay, or we could do it this way with 30 times 50 and break that out into 30 times 6 times 5, and then break the 6 into 2 times 3, and then the 50 is 5 times 10, and break the 10 into 2 times 5. So we're creating what we call a factor tree, and we stop when we get prime numbers and just circle them. So those leaves are our factors. Okay, but either way you do this, you're going to get 2 2s, a 3, and 3 5s. Okay, this should be up here. This should be 2 to the second power, not 22. And this should be 5 to the third, not 53. Okay, so those should be exponents there. Okay, so we're just using exponents to summarize all that. Okay, our second method is just by division. So we want to look at the smallest prime number which goes into our numbers. So we divide the given number by the smallest prime number by which is divisible. So if it's an even number, we start with 2, and then we'd see if 3 goes into it if we're done with the 2's. Okay, I'm going to place our answer under the given number, and then divide that, our answer is our quotient, and then divide that quotient by the smallest prime number by which is divisible. In other words, we still have an even number, we would divide by 2, and again, we'll record this quotient. Okay, and you just keep repeating until the answer is a prime number. So we just keep going until we get a prime number. So here's our example for 1500 using method 2. We start with 1500, and we know we start with our prime numbers. So remember, our prime numbers are this: 2, 3, 5, 7, 11, etc. We probably don't need to go farther than that, right, for this one. So so we start with 2. Yes, 2 goes into 1500, and we divide by 2, we get 750. So there's our answer. And then we can still divide by 2, right? So we're going to divide again. Okay, so that we divide 750 divided by 2, we get 375. Okay, now we know we don't have an even number, right? And we know 5 goes into it, but check 3 first. So add our digits. 7 plus 3 is 10, plus 5 is 15. So 3 goes into this number. So the next one would be 3. Okay, and then we divide that, we get 125. Okay, now we know we don't have an even number, right? So 2's not going to work. Try 3. 5 plus 2 plus 1 is 8. So 3 doesn't go into it. So the next one is 5. So 5 goes into that 25 times, and then finally 5 goes into 25 5 times. Okay, so that's our last one. We're going to use all the quotients. So we have 2 2's, a 3, and 3 5's. Okay, so 2 times 2 times 3 times 5 times 5 times 5, or 2 squared times 3 times 5 cubed. So that's the division method as opposed to the tree method. Okay, let's talk about the greatest common divisor. Okay. The greatest common divisor is GCD, sometimes we say. It's the largest natural number that divides without remainder every number in its set. Okay, so we're going to look at the set of natural numbers, and we're going to look at the biggest number that goes into all of them, that divides into all of them. Okay, so in order to do that, we first find the prime factorization of each number, okay, of it in our set, okay, and then we list each prime factor with the smallest exponent that appears in each of the prime factorizations, okay, and then from step 2, we determine the product of the factors found in step 2. Okay, so we're going to use common factors that are in each one, and in doing that, we're going to look for the smallest exponent that appears in each of the prime factorizations. Okay, so for example, let's say we have 54 and 90. Okay, if we do our factorization, we get 54 equals 2 times 3 times 3 times 3, or 3 to the third. 90 is 2 times 3 times 3 times 5, or 2 times 3 squared times 5. Okay, and we're going to look for common factors. So we have a 2 in both. Okay, so that we'll use 2. And then we have 3 in both, but we're going to use the smallest number of occurrences. So that would be 3 squared, not 3 cubed. Okay, so 9 goes into this one, but 27 doesn't go into this one. So we would just use a 3 squared, smallest exponent. We don't have a 5 in both of these, so we wouldn't use the 5. So we're just going to use 2 and 3 squared. So our greatest common divisor is 2 times 3 squared, or 18. So that is the biggest number that goes into that. And let's say we had a fraction. We have 54 divided by 90. What we can do, is if we want to simplify that fraction, is divide by that GCD on the top and the bottom. So if you divide by 18, which is the greatest common divisor, on the top, and divide by 18 on the bottom, we get 54 divided by 18 is 3, and 90 divided by 18 is 5. Okay, and that would be our simplified fraction. So one place we use the greatest common divisor is to simplify a fraction. We're looking for the biggest number that divides into both of these. Okay, and that would be 2 times 3 squared, or 18. Okay, least common multiple is kind of the opposite idea. We're looking for the smallest number that both of them divide into. Okay, so we're looking for the smallest number that both of the numbers divide into. Okay, for least common multiple. And you can think of least common denominator when we're talking about fractions. Okay, so it's the smallest natural number that is divisible by each element of the set. Okay, so each element of the set goes into this, whatever this number is. Okay, so to determine this, we again start by determining the prime factorization of each number. Okay, and we're going to list each prime factor with the greatest exponent that appears in any of the prime factorizations. So we're going to use all factors, okay, that appear. But if we have them in both, we use the one with the greatest exponent. And then we find the product of the factors found in step 2. Okay. Getting back to our example with 54 and 90, remember 54 is 2 times 3 cubed, and 90 is 2 times 3 squared. We have a 2, so we're going to use it, and we use the highest exponent. Well, both of them are 1, so we're going to use just 2 to the 1. Okay. We also have a 3, and it happens to be in both. We're going to pick the highest exponent of 3, so 3 cubed. And we also have a 5, so we're going to use that. So look for every factor that you see, including the 5. So for least common multiple, we use every factor that we see, and if we've got it in both, we use the one that has the most. Okay. So a 2, a 3 cubed, and 5, which is 2 times 3 cubed times 5 is 270, or 5 times 2 is 10 times 27 gives us 270. So that's our least common multiple. Okay. So a place where you might see that would be with a fraction. So let's say we're adding a fraction with 54 as a denominator, 90 as a denominator, so 2 fractions. Let's say 1 over 54 plus 1 over 90. Okay. So we'd use that least common multiple as our greatest common denominator here, least common denominator. So that would be 270. Okay, so we're going to have to multiply times 5 here to get 270, which we do the same thing to the top. So 1 over 54 becomes 5 over 270. And then we multiply 90 times 3 to get the 270. So 3 times 1 is 3, and 3 times 90 is 270. So now that we have a common denominator, we can add our numerators. Remember, we add fractions, we have to have a common denominator. So 5 plus 3 would be 8, so that would be 8 over 270. So here's where we use our least common multiple if we're adding fractions with different denominators, 54 and 90, for example. There is, in fact, no largest prime number, and this was proved by a Greek mathematician, Euclid, over 2,000 years ago. Okay, so Euclid proved that there is no largest prime number. Okay, so we continue to strive to find larger and larger prime numbers. Okay, and a lot of mathematicians work on this. It's not an easy thing, actually. Okay. One mathematician, Marin Mersenne, from the 17th century, found that numbers of the form 2 to the n minus 1 are often prime numbers. Okay, when n is a prime number. Okay, we call these Mersenne primes. Okay, so 2 to the n minus 1. So let's say, for example, let's just do a simple one. Let's say n is 5. We know 5 is a prime number. If we take 2 to the 5 minus 1, 2 to the n minus 1, okay, is 2 to the 5 minus 1, which is 32 minus 1, which is 31, which is also a prime number. Okay, so that's kind of an example of how we would find another prime number. Now that doesn't always work. So but we're saying they're often prime numbers. So it's not a foolproof thing, but it works a lot. Okay, so that's one way to find larger prime numbers is take n as a prime number, whatever it is, and take 2 to the n and then subtract 1. The first 10 Mersenne primes occur when n equals 2, 3, 5, 7, 13, 17, 19, 31, 61, 89. Okay. The first time it does not generate a prime number is when n is 11. Okay, so 2 to the 11 minus 1 is not prime. Okay. So there's an exception. So it doesn't always work. We did it for 5. Remember, we did 2 to the 5th, and we got 32 minus 1 is 31. So here's where you were using these ends, 2, 3, 5, 7. So we can see the next prime here would be 11. It doesn't work, right? 17, 19, 21 would not work. Or sorry, 21 is not a prime number. 23 would not work. Okay, so the next one would be 23 because it's not there. The next one after that is 31 that does work. So not all of them work. You know, there's some prime numbers. You know, 23 and 29 are also prime numbers in here. So 37, for example, after this. So it doesn't work for all prime numbers. Okay, the largest prime number so far was discovered January 25th, 2013 by Curtis Cooper, math professor at University of Central Missouri, and he found this one, 2 to the 57,885,161 minus 1. That's a really large number. You're taking 2 to a 57 millionth power. Okay, it's 17 million over 17 million digits long. Okay. If you write it in 12-point font, it's almost 23 miles long. So that's how long the number would be to write. So very large. But that's not an easy thing to try to prove that this number is a prime number. That it's a really large number, right? This is how many digits it has, 17 million digits. So that requires a lot of computing power, and it requires very sophisticated algorithms and methods to determine if something's a prime. We just can't use our standard factor tree, for example. Okay. So it gets very complex when we're trying to find these large prime numbers. Fermat's numbers, Pierre de Fermat was a mathematician from the 17th century, conjectured that each number of the form 2 to the 2 to the n plus 1, which is we call a Fermat number, was prime for each natural number n. Okay. The conjecture is a hypothesis that has not been proved or disproved. So it hasn't been proven yet, but it hasn't been disproved either. Remember we talked about deduction? Well, no one's disproved it by deduction. So we haven't disproved it yet. Okay. So this is a little bit more complicated because we're talking about 2 to the 2n plus 1, not just 2 to the n. Okay. So, like for example, let's say we have our n is 3. Okay. So 2 to the 2 to the n plus 1 would be 2 to the 2 to the n plus 1. Now 2 to the n would be 2 to the third, right? So it's 2 to the 2 to the third. So this actually 2 to the third is our exponent. So that would be 8. So it's actually 2 to the 8th plus 1. 2 to the 8th is 256, and we have one, we get 257. So that's actually a prime number. So, and as far as you go, you'll find prime numbers by doing that because it hasn't been disproven yet. So it's been tried for very high values of n. But you can see how quickly this gets big. You start with n equals 3, and you get 257 as your prime number because you're taking 2 to the 2 to the n. So you're taking this exponent, and you're taking the exponent again. Or maybe not. In 1732, Leonard Euler, who was a famous mathematician, proved that for n equals 5, which is 2 to the 2 to the n would be 2 to the 32 plus 1, that's a composite number. Okay. So he actually disproved Fermat's conjecture. Okay. So since Euler's time, mathematicians have been able to evaluate only the 6th, the 7th, 8th, 9th, 10th, and 11th Fermat numbers. Okay. And each of these has been shown to be composite. Okay. So, so if you go to higher orders, 6, 7, 8, 9, 10, 11, these get big really, really fast. They actually are composite numbers. So, and we've only been able to go to 11. So we've only been able to do the 11th one. Here's the 5th one. I did the 3rd one. I did n equals 3. The first one would be n equals 1, right? Which would be 2 to the 2 to the 1, which is just 4 plus 1, which is 5. But as you get bigger, these get, as you go up from n to 5 to n equals 6, these get big super fast, okay? And mathematicians have only been able to do up to n equals 11. But it stopped at n equals 5. You think about, I mean, that was the first exception, okay? And then when you go beyond that, they were shown to be composite, so they weren't prime, okay? So Fermat numbers only went up to n equals 4 as far as we know, okay? I'll do n equals 4 in class just to show you. Okay, in 1742, Christian Goldbach conjectured, again, that's not proven or disproven, that every even number greater than or equal to 4 can be represented as the sum of 2 prime numbers, okay? Not necessarily distinct, okay? So they could be different, okay? Or they could be the same. So, so for 4, we could write as 2 plus 2, they're both prime. 6, we could write as 3 plus 3, they're both prime. 8, we could write as 3 plus 5, those are both prime. 10 is 5 plus 5, those are both prime. 12 is 5 plus 7, okay? Those are both prime. So we could say is every number, we can do this for every number, greater than or equal to 4, okay? That we can add, show as a sum of prime numbers. We have not proven or unproven this to this day. So we haven't proven it, but it hasn't been unproven to this day. Okay, if we have primes where we have p as one of the primes and p plus 2 is the other one, okay? For example, 3 and 5, or 11 and 13, where one is 2 more than the other, we call those twin primes, okay? So 5 plus 3 is an 8. 11 plus 13 is 24. Okay. This conjecture states that there are an infinite number of these pairs of twin primes. Okay. The largest known twin primes are of the form 3 million. Sorry, not 3 million. 3,756,801,695,685 times 2 to the 666,669th power, plus or minus 1. We're saying, where do these, where do we have primes that are right next to each other as far as odd numbers, right? 11, 13, and 3, 5. Well, they can get really big, that there's an infinite number of these pairs, okay? And we actually had, research, mathematical research that found this number. And this is a super huge number. We're taking this number times 2 to this giant power, and then saying plus 1 would be the odd one, the higher odd one, and minus 1 would be the lower odd one. Okay, and these were 2 research groups that did this twin prime search and prime grid, and this was back in 2011. Okay, so just to give you an idea of some of the mathematical research, not necessarily to an obvious useful end, but actually they're these can be useful research. But just some of the research that trying to find higher prime numbers and higher prime numbers that are kind of next to each other. They're only 2 apart. Okay, and this is what we mean by them being 2 apart: 3, 5, 11, 13. Okay, so 2 in a row basically that are odd. Okay, and this is the research that discovered this giant one so far. Okay. All right, we'll do some factorization in class, and we'll look at some examples of, how we can do some of these to find prime numbers. I'm not going to ask you to memorize names or this section, but I do want you to be able to factor and find least common multiple and greatest common divisor. Okay?